Welcome to the healthaibrief, breaking down the AI shaping our world one concept at a time. In the last couple of episodes, we introduced the core concepts of supervised and unsupervised learning, with supervised learning being the star student learning from a perfect set of flashcards prepared by an expert. But what if you only have a few flashcards and a whole library of unlabeled books? In medicine, this is the norm. Expert labeled data is the single most expensive and time-consuming part of building an AI. Today, we're exploring a toolkit of smart solutions to this very problem. We'll cover 3 powerful methods that allow AI to learn from imperfect, incomplete, or noisy data: semi-supervised learning, self-supervised learning, and weak supervision. So let's start with the most common scenario. You have a little bit of high-quality labeled data and a mountain of unlabeled data. The analogy here is a medical student preparing for a major exam. The professor gives them a study guide with just 10 complex cases that are fully solved, showing the diagnostic process from start to finish. This is your precious labeled data. The student also has access to the hospital's entire archive of 10,000 other patient cases, but with no answers attached. This is your unlabeled data. So a semi-supervised approach is like the students. They first master the 10 solved cases to understand the fundamental patterns, then they apply that initial knowledge to the vast archive of unsolved cases, making educated guesses and identifying the cases that look most similar to the ones the professor provided. The model's most confident predictions are used as temporary kind of pseudo-labels. Now the student or the AI retrains on a much larger dataset, combining the original expert labels and its own high-confidence pseudo-labels. It's a powerful way to let a small amount of expert guidance shape the learning process across a massive dataset. Now, what if you have no expert labels to start with? How can a model learn anything useful? This is where the almost magical technique of self-supervised learning comes in. Imagine a pathologist in training who's given a single high-resolution digital slide of healthy tissue and is told, learn what this is supposed to look like. To do this, they invent a game for themselves. They take the image, digitally cut it up into 100 pieces like a jigsaw puzzle, and then task themselves with putting it back together correctly. This is exactly what self-supervised learning does. The AI is given a task where the answer is inherent in the data itself. No human is needed to provide a label. In order to solve the jigsaw puzzle, the AI must learn the fundamental structure of the tissue, what cell boundaries look like, how blood vessels are shaped, the texture of different cellular groups, for instance. It creates its own supervision by solving this pretext task. It develops a rich understanding of the data's grammar. The foundational knowledge can then be used as a powerful starting point, allowing a specific diagnostic model to be trained with far fewer expert label examples later on. The final technique tackles the problem from another angle. What if we have labels but they aren't precise? Manually drawing a boundary around a tumour on a CT scan is slow, but what about the radiology report that's already been written for that scan? This is the core idea of weak supervision. Instead of precise hand-drawn labels, we use noisy, programmatic or less exact sources of information. For example, we could train a model by teaching it that any CT scan whose corresponding reports include the phrase nodule in the right upper lobe gets a weak image level label of nodule present. This label doesn't say where the nodule is, but it provides a useful scalable signal. And by applying simple rules and heuristics like this across thousands of existing clinical reports, we can generate a massive, albeit imperfect, training dataset almost instantly. It's a pragmatic trade-off. We sacrifice label detail and quality for enormous scale. So whether it's using a few solved cases to understand many, solving a jigsaw puzzle to teach itself, or learning from the noisy keywords in a clinical report, these techniques are essential for bringing AI out of the textbook and into the messy, complex reality of healthcare data.